Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics in the chapters of mechanical actions, equilibrium of a body, and Archimedes' upthrust. This exercise was a previous one in the brevet exams in 2006 second session, third exercise. The title of this exercise is floating objects. Is it easier to swim in the fresh water of a lake or in seawater? So as we can see that the opening of this exercise is a question. To answer this question, we perform the two following experiments with a solid S of mass m is equal to 2 kilograms. So the mass of the solid is given by 2 kilograms. And given G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Part A, first experiment. S floats at the surface of the water of the lake of density 1000 kilogram per meter cube. So here, because it's floating at the surface of the water, so we can use at any moment in this part the condition of equilibrium. Moreover, given that the density of the lake, let's denote it by rho lake, is given by 1000 kilogram per meter cube. Number 1. What condition must the two forces acting on S satisfy so that it floats at the surface of water? In other words, they are asking me about the condition of equilibrium. How do I apply this condition? Always as a title we will write at equilibrium. And on the left hand side of this equation we will write the sum of forces acting on the solid S. So what are the forces acting on the solid S? Because it has a mass, then it will be directly subjected to the weight vector. And because we have the liquid here, the liquid is represented by the water of the lake, then it will be directly subjected to the Archimedes upthrust force F upthrust. And on the other side of this equation, we write the zero vector corresponding for the condition of equilibrium. And we don't forget zeros on all of these quantities because this is a vectorial equation. Now moving F upthrust to the right hand side, we have the W vector is equal to minus F upthrust. So what does the first equation tells us? That the effect of both forces acting on the solid S cancel each other, whereas the second equation given by W vector is equal to minus F upthrust tells us that both forces have the same line of action, the minus sign for the opposite direction, and same magnitude. And here let me clarify the following. Because this weight is represented by a vector and we have a liquid, we must distinguish between two types of weights, the real weight and the apparent weight. But whenever we are discussing the weight as a vector, we always mean the real weight and not the apparent weight. Okay, so this weight vector represents the real weight. Now in number 2, calculate the value of the weight of S. Deduce the value of the Archimedes upthrust. So let's start by the first part, in which we want to calculate the value of the weight of S, and by the value they mean the magnitude. So given the mass of the solid S and given the value of G, the magnitude of W vector can be calculated using the following formula, that W is equal to M multiplied by G. Now the value of M is given by 2, the value of G is given by 10. Plugging this on the calculator, then the value of W is given by 20. Since both M and G are in the SI, so the value of W will be in the SI, which is in newtons. Then W is equal to 20 newtons. As for the second part, deduce the value of the Archimedes upthrust, and here by the value it means the magnitude, and by deduce it means that we need to refer to the previous part in which we have determined the value of weight, knowing that we have the condition of equilibrium. So W vector is equal to minus F upthrust, and we are interested in the magnitude, so let's write in magnitude. Now here what we will do, we will drop down the vectors and remove the minus sign, so we have that W is equal to F upthrust. But knowing that the value of W is given by 20 newtons, then the value of F upthrust is given by 20 newtons as well. Then let me write here that the value of W is given by 20 newtons, for example. Now in number 3, calculate the volume V1 of the immersed part. So we know that the volume of the immersed part and the value of F up thrust are related via the following formula. That the magnitude of F up thrust is equal to the density of the liquid times the volume of the immersed part times G. We are interested in determining the value of VI. So constructing the triangle of this formula, here because we have multiplied and F up thrust will be at the top, rho L, VI and G at the bottom, we are interested in determining the value of VI. Putting our hand over VI, then the immersed volume, which is denoted by V1, is given by the value of F up thrust divided by the density of the liquid. In this case, the liquid is represented by the water of the lake. So rho lake for the liquid multiplied by the value of G. The value of F up thrust is given by 20. The value of the density of the lake is given by 1000. And the value of G is given by 10. Plugging this fraction on the calculator, then the volume is given by 2 times 10 to the power minus 3. Since all of these quantities F up thrust, rho lake and G are expressed in the SI, so the value of V1 will be in the SI, which is meter cube. Then the volume V1, when the solid S is immersed in the water of the lake, is given by 2 times 10 to the power minus 3 meter cube. And let me write here that the volume of the immersed part is given by 2 times 10 to the power minus 3 meter cube. Now in part B, corresponding for the second experiment, S floats at the surface of seawater of density 1040 kg per meter cube. So now the density of seawater, let me write here rho C, is given by 1040 kg per meter cube. And notice here the difference between the densities between that of the lake, which is considered water, and the density of the sea. So the density of seawater is given by 1040, which is considered to be salty. Due to the presence of the salt, the density will increase from 1000 to 1040. Now part 1. Now here they are telling me that S floats at the surface of water, so we can use the condition of equilibrium at any time. Number 1, Archimedes up thrust remains the same. Why? So they are telling me that the value of F up thrust is also given by 20 newtons, which is the same that we have determined in part 2 in the first experiment, part A. So they are giving me the answer that F up thrust is equal to 20 newtons, but since they are telling me why, so it's required to justify. So let's say, since S didn't change, so what do we mean that S didn't change? So we didn't change the solid S, so its mass remained the same and it is at equilibrium. And here by equilibrium we mean the equation or the equality between the magnitudes, which is given by weight is equal to F up thrust. So because we didn't change S, so the mass didn't change, then the value of W didn't change, then in this case F up thrust will remain equal to W, which is given by 20 newtons. Then the value or the magnitude of the Archimedes up thrust remains unchanged or remains constant, remains the same. Then the value of F up thrust is given by 20 newtons. Now here notice that they are telling me Archimedes up thrust remains the same. Why? So they are referring to this as the force which is given by F up thrust having the Piltdown properties, but knowing that the line of action and the direction doesn't change, so always F up thrust acts vertically upward. So in this case they are asking me about the magnitude or the value and not about the other properties. Now in number 2, calculate the volume V2 of the immersed part of S. However, in this case, because it doesn't mean that F up thrust didn't change, the volume V2 of the immersed part will not change, because we know that the volume of the immersed part is related to F up thrust via the following formula. And in this case, we are interested in determining the immersed volume. The immersed volume doesn't depend only on F upthrust and G, but also depend on the density of the liquid. So whenever we change the density of the liquid, the volume of the immersed part will change. For this reason, they are telling me again to calculate the new volume V2 of the immersed part. So let's construct the triangle of this formula. Here, because we have multiplied, then F upthrust will be at the top, rho L Vi and G at the bottom, knowing that we are interested in determining Vi. In this case, it's denoted by V2, which is equal to F upthrust divided by the density of the liquid. Now notice that in this experiment, the liquid is given by the seawater, and the density of the seawater is given by rho C, multiplied by the value of G. So F upthrust is given by 20 newtons, which remain the same, divided by rho C, which is given by 1040, multiplied by the value of G, which is given 10. Plugging this fraction on the calculator, then the volume of the immersed part is given by 1.92 times 10 to the power minus 3. Since all of these quantities, F upthrust, rho C, and G, are expressed in SI, so the volume of V2 will be expressed in SI, which is meter cube. Then the volume V2 of the immersed part is given by 1.92 times 10 to the power minus 3 meter cube. Now part C, answer for the question. So depending on these two experiments, we need to refer back to the first question to answer it. Now, knowing that swimming is easier when the immersed volume of the floating object decreases. So what's meant by this? So having several immersed volume, when the immersed volume is the smallest, this makes swimming easier. Is it easier to swim in the fresh water of a lake or in the seawater? Why? So here we have two immersed volumes. V1 is given by 2 times 10 to the power minus 3 meter cube, corresponding to the water of the lake. And we have that V2 is equal to 1.92 times 10 to the power minus 3, corresponding to seawater. So in order to determine whether it's easier to swim in the water of the lake or in the seawater, we need to compare the corresponding immersed volume. So knowing that V1 is equal to 2 times 10 to the power minus 3 meter cube, and V2 is given by 1.92 times 10 to the power minus 3 meter cube. And here by compare, we need to say whether V1 is less than V2, equal or greater, knowing that they have the same unit, so we can compare the numbers directly. Now in this case, V2 is less than V1, or we can say that V1 is greater than V2. So the immersed volume corresponding to seawater is less than the immersed volume corresponding to the water of the lake, which means that swimming is easier in the seawater. Then let's say since the immersed volume of the object in seawater is less than that of the lake, then swimming in seawater is easier. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.